Hi, my name is Michael Taylor, and today my talk is entitled Your Agile Open Source Hardware Stinks Because Is It Not a System? And it's further subtitled A Talk About Open Source Unhardware. So the goal in this talk is to talk about kind of the non-hardware aspects of executing a successful open source hardware project. And so I'm going to talk about a bunch of the projects that we've executed in my group and some of the lessons we've learned from them. And then we're going to talk about a meta-analysis of open source hardware generally and what some of the key things to think about are. So part one, journeys in open source. So this is a subset of the open source projects that are going on in my group. The kind of the foundation of my projects are the BaseJump STL standard template library for Systemerlog. So it's a collection of commonly used hardware blocks. Pretty much all of the things that you regularly compose on hardware, we have implementations of them, and more importantly, we have standardized interfaces that allow these things to connect together very easily and without bugs. We also have a collection of open source portable physical IP, including an open source DRAM controller and PHY, and an open source clock generator, and then open source high-speed links, for example, for going to an FPGA. So these components are really some of the stumbling blocks in building a high-performance ASIC prototype. And so we've been developing this in the group, and then other people have been using them in their prototypes. We've also been working on some open source machine learning blocks like tensor cores. In addition to the BaseJump STL project, we also have a project called BaseJump Accelerator Socket. And the goal there is to handle the problem of I/O and memory system for new accelerator designs that are being prototyped in research. And so basically, you can focus on designing the accelerator, and then we have a standard interface that you hook up to, and then that will give you essentially a packaging solution, a motherboard for your accelerator, PCIe connection to a Linux server in a Xeon host. So the whole thing, the whole I/O system, the drivers, the firmware, everything has already been pre-designed for you. So then you can focus just on what goes in the center of your chip and what's your value add in terms of an accelerator. We also have some projects which are focused around processors that are open source. So we have the BlackParrot open source RISC-V Linux multi-core. And we have Hammerblade Mini-Core, which is an open source, energy efficient, high performance compute fabric. And then finally, I'll just mention that we have a small project, which is a System-Verilog to Verilog converter, which some people who develop in System-Verilog may find it useful to use in order to release their code as Verilog so that open source tools can use it, because many open source tools don't yet support System-Verilog. So I'm going to talk first about one of the early projects that we had, which was quite successful technically. So it's called Celerity, and it was really probably the first open source RISC-V mini-core. It had 496 32-bit RISC-V compute engines running at 1.5 gigahertz in TSMC 16. It also had 5 Linux capable RISC-V cores, the Berkeley Rocket cores, and then it had some 10 always-on cores, and then a neural network accelerator. So there are 511 RISC-V cores in total, and it broke the world record for performance on the CoreMark benchmark suite. With only 12 millimeters of silicon, it beat every other piece of silicon in the world. In addition, we also still hold a world record, probably by orders of magnitude, for RISC-V instructions per second in a single chip. And you can see the die photo down in the corner of a single tile. It's super area efficient. You can see the 2 RAMs there. There's a 4K instruction RAM and a 4K data RAM. And then the logic, which includes the register files, is quite small comparatively. This is, in terms of performance efficiency, this is hitting 40 cores per millimeter in 16 nanometer. So it's an astounding density. This would be 120 cores per millimeter in 7 nanometer. But despite that success, we did encounter some interesting things that happened, after we got the chip back and we brought it up. One of the things was that although this is actually one of the most programmable many cores that ever developed in academia, by ordinary user standards, it still has a long way to go. So in fact, we had 2 postdocs and a research scientist working for a week to get the CoreMark benchmark up and running. And that's a lot of expertise required to get a benchmark of medium complexity going. And so kind of what we realized is that as a research project, Celerity was very successful, but as an open source project, open source hardware project, we really need to think about the system level. It's not just the awesome diamond we've created in terms of hardware. It's also how easy is it to use and programmable and all of these other things which are crossing over into the into software and even packaging, software packaging issues. And so kind of the lesson here is even if you execute your open source hardware project flawlessly from a technical perspective, there is a lot that remains in order to get other people on board and using it and putting it into systems. So currently we're working on a follow-on project to Celerity, which is called Hammerblade. And Hammerblade really is focusing on the software and the usability. And so we've been, from the hardware perspective, really architecting it around maintaining the amazing efficiency it has, but also adding in programmability, really thinking about what features are going to lead to high performing code, with minimal effort from users who have only a modest amount of programming experience. And so part of that is we're also building a bunch of domain-specific library ports on top of Hammerblade. So we have PyTorch running on Hammerblade, we have TVM running on Hammerblade, those are ML infrastructures, and then we have Graphit, which is a framework for graph processing from from MIT. And all of this runs on top of a CUDA-like language we call CUDA Lite, which maps very efficiently to the mini core and provides a familiar C++ programming model. So you can kind of see, how Hammerblade evolved in terms of, we had a technical success from Celerity, but then we really pivoted the project focusing around the system level aspects of the hardware. It's influencing how we do the hardware, but really in order to envision success, almost all of the problem is actually around the software that's enveloping the hardware. We have another system called BlackParrot, which is focused not on being, hundreds of cores, but being a standard cache coherent multi-core processor that runs Linux. And we've had some interesting experiences there. And a lot of the project is not just in the technical aspect of developing a high quality core, but around a lot of the aspects of open source, a lot of the facets of open source and how you can create success from an open source perspective. So let me talk a little bit about that. So our goal with BlackParrot is for it to be the kind of Linux of RISC-V. So it's supposed to be the community maintained Linux core. People can come along and improve it, do pull requests. We integrate in the pull requests, and over time, the whole world is crowdsourcing this awesome RISC-V implementation. And as part of our research for doing that, we've been thinking a lot about how do we develop hardware in a way that kind of combines good ideas from software engineering, but not too many of them, in particular, leaving out the ones that are going to make it hard to get good power performance in area, or they're going to be challenging for hardware developers to use. And then, in general, we want to be, easy to use and flexible, transparent, and basically create a platform that accelerates innovation by allowing people to rapidly prototype new ideas in something that's very high quality. And so there's a kind of idea of being the LLVM of processor design as well. So these are lofty goals. And so I'm going to talk a little bit about some of the ideas and principles that we've been using and to guide us on our path. So we have 4 metrics for success in the BlackParrot project. So one is, the most important one is the quality, is how will people trust our code, right? So can they look at it and understand it easily? Does it seem to be securely written? Is it validated? Would you trust putting it in silicon and relying on it? And later on in the talk, I'll talk more about this trust issue. And then also virality. So we want to make sure that people just feel naturally compelled to use the code in our project. Can we convince people to join the project? Can we scale to lots of users? Can we convince companies to invest and become stewards of the code? Because ultimately we want to transfer the ownership and to diffuse the ownership of the code across the entire world. So we're really thinking of ourselves as just doing like the initial version from which there can be continuous improvement. And then, of course, you need to fulfill some needs that people have. So functionality is really important. And I think in our project, we're a little bit different in terms of, we also think about what functionality people don't need. So we want to really keep the code base small and avoid adding in complexity and features that actually are not going to be widely used. And then finally, efficiency. This is usually the one you think of first when you design hardware. We list it fourth, but of course, power performance and area is important as well. So then, as we develop the code, we have kind of 3 rules of thumb that we use in order to guide decisions where there's a tie break that's involved. So one is be tiny. So if you're choosing between 2 alternatives, pick the one that's smaller in terms of the amount of code and maybe the area. Be modular. So then if we can compose our hardware out of many blocks that can be reasoned about independently, then that means that someone can contribute to the project without understanding all of BlackParrot. And then finally, this is probably the most important one, is be friendly. So we want the code to be friendly to the user, but we also want to be friendly to people's contributions, which can be very problematic on online communities, including Linux. And so in terms of the technical feature set, we are focusing on a multi-core host for accelerators. So this is supposed to be very area energy efficient. It's supposed to kind of be on the side, not the main show, not a server processor, and it's going to be there to host and take care of accelerators that people are designing and need some kind of host core to run Linux to maintain those accelerators. So now I'm going to talk about a final project, which is the BaseJump Accelerator socket project. And just to give you an overview of that, so if you think about designing an accelerator, you might think of it in this way. There's basically 5 kinds of people that you need to do it. So you need someone who can understand the application domain. You need someone who can design architecture. You need an RTL developer. You need somebody who can do the I/O, the plumbing, and then you need someone to tape out the chip. But really, there's actually 5 more kinds of experts that you need. You need someone who knows packaging. You need someone who can specify socket, someone who can design a motherboard, someone who can lay out a motherboard, someone who can write FPGA firmware, someone who can do PCIe Linux drivers, and someone who finally who can interface the application to Accelerator. So this would be someone modifying PyTorch to use the Accelerator. So that's a lot of experts to try to acquire just to execute an Accelerator project. And my hypothesis is that having this many required experts really reduces the number of ideas that collectively the world can try out. And so with BaseJump, we are basically getting rid of 5 of these kinds of experts. So we've already pre-designed these components, so you can just use them, and then you can focus on mostly on the implementation of the Accelerator itself, and then also how it interfaces to software, which of course is part of the process of building the entire system. So, so we have a bunch of components for BaseJump, and I'm going to just briefly show it here. So up on top are the 5 kinds of experts you need, and then down on the bottom is the infrastructure that we've designed. We have a custom package, custom socket for that socket, that package to go into, a custom motherboard and firmware, and then of course this can plug into a standard Linux server and run the customized Linux PCIe drivers that we've created. And interestingly, because we've manufactured all of these things, or order them on the web anyways, they're actually all commercially available. We just have to give you the build number for the component. So if you want to order one of those motherboards, we just give you the build number, and then Sierra will go order the parts and assemble the board for you. So it's actually a pretty interesting case where open source is not just a GitHub repository, it's also a set of components that are orderable just from standard manufacturers, creating a physical supply chain. And we've had a bunch of users of BaseJump, the Accelerator sockets, and these are external users, including University of Cambridge, University of Michigan, Princeton, MIT, and Cornell. And people have used all of our stuff without changing it. People have also customized individual components. Maybe they take the open source motherboard and add some features to it and then fabricate that. So it's a very flexible ecosystem for people to work in. And I think one of the reasons we've seen adoption is because we solved our own problem, and it's a problem that's in common, across many people who are building prototype chips. And our solutions are, at least slightly better than the things that other people come up with, because we put more effort into it than most people would be willing to put into it. So now I'm going to talk a little bit about meta-analysis, stepping back, thinking about these projects. And I think, thinking about the best analogy for open source, and I think it's one of these open-ended games. So this is a picture of a old game I used to play when I was a kid called Pirates. You would, sail around the Caribbean, and you could outfit yourself with better ships. You could negotiate deals with different islands. There were other boats that you might get into conflict with, but it was pretty much, up to you where you went. And I think that's part of the challenge of the open source project, is that there's actually a huge universe of things you can do. There are different things you can optimize for, different ways you can package what you're doing for different audiences, different users that you can target. And so, you can think of yourself as the captain of the ship going through this vast ocean. There's your open source project. And then, you can go out into the open seas and do whatever you want, but you might also starve and die by running out of resources for your project. Maybe you don't have any more funding, or your crew abandons you. You don't have anyone working on the project anymore. Maybe they graduated with their PhD or something. And so because of that, those kind of constraints, even though it's an open-ended game, you actually have to be quite strategic about what your goals are in the game and accomplishing them. And so, just like in this game world, there are people out there who are potential users or investors in your open source projects, and your goal, at some level, is to figure out who they are and what they would work best for them, and then to steer your ship, your open source project towards those needs. But then, of course, there are other boats in this universe too, and in the case of open source, those are people who are kind of building the same thing that you're building, but doing it their way. So, and I think this is just a reality of open source. Is whatever you're doing in open source, there's always someone else. There's always a BSD for for Linux, or there's always alternatives, and so there's a kind of a competitive space there for you to figure out what features you're gonna put in there to differentiate, right? And what is it that you're going to do differently than everybody else in order to make your project successful and used. Or you might just decide to do things like you can do in the game, like make alliances or join forces or get into conflict with them, right? These are all possibilities. Hopefully, everybody steers their ship in a way that is productive for the world. So there's some hard questions for people doing open source. So the first question, and I ask these hard questions of myself almost every day: does my hypothetical future user really exist? So a lot of open source, I think, is built on the premise, build it and they will come. But who's they, and will they really come? Do they even really want what you have? And so I think sometimes that it might be a better approach to say, can I get anybody right now in the world to use this thing, and not by paying them money to do it? And what are they going to do with it? That might be actually a better guide than a hypothetical user that is going to show up 2 years after you're done with the project or something like that. Like who would use it now? I think can be a really good motivator for steering your ship. And so there's some surprising things. So like, for example, the Celerity open source design that I mentioned, the main people who picked it up are actually commercial CAD vendors who need some really big designs to test emulation and simulation speed. Kind of surprising. I'm not sure if I would steer my boat more in that direction, but it is a concrete user, and they actually are the ones that generate the most feedback for our project if they're actually using it. Of course, we use our own stuff internally, and so that's always a great source of feedback on what you're doing. And then it's also very intriguing to think about under what conditions will commercial companies actually use your open source IP. And then also, what is the mechanism by which we discover new kinds of users where we could add new features to support them? And so I think, you know, as part of that process of just grabbing whoever it is who's willing to work with you and working with them, it will force you to think about, instead of like making, you know, your processor high performance or whatever it is, what are the things that are actually missing that would prevent them from using it that are probably totally unrelated to the, you know, the technical parameters of your design, right? So, and it'll force you to go do those things. So these kind of things that we found are like, you know, AXI converters or whatever it is, you know, Wishbone, people want to plug processors into things. Untethered setups, you know, all of our stuff is built to be, you know, used in a lab as test chips or test systems. That's very different than a standalone chip in terms of how you do some of the plumbing. And then finally, as I mentioned, the software that you need to use the hardware, which could be about building the binaries or debugging, interfacing and debugging your chip, all the way up to like, how do I write parallel programs on this piece of hardware? This kind of thing is really the kind of infrastructure that's going to influence whether people use your stuff. And then this one is really intriguing, which is how will you make the project persist after whatever the current conditions are that created the open source project end? So it could be the students, the key students graduate, the research grant ends. You get a family, don't have time to contribute, you know, half of your time to the open source project. These kinds of things are, you know, could be the kiss of death for your open source project. And so, you know, here are some ideas that other people have thrown around that I've heard, you know, the idea of having a lifetime maintainer. So maybe the lead developers graduate and they can bring a project with them to their next employer and say, hey, I want to work for you, but I also want to spend 50% of my job, you know, improving Python or, you know, Linux or whatever it was. Those are historical cases, but whatever the, you know, your open source project is. Of course, you can keep it alive inside your own research group if you actually have a need for that infrastructure and it's not just a pure research project. Generalized commercial adoption is kind of, I think, the hardest thing to envision and really hard to figure out and to meet with the commercial users' needs and beat what their alternatives are. And then, you know, the last is this kind of startup freemium model where, you know, everybody graduates and then we do a startup, right? And we say, well, we'll keep the old version around and keep it maintained so people can still use the free version, but we're going to figure out a way to charge money. I think it kind of kicks the can down the road. Eventually, there'll be some constraints that will make it very difficult to continue it as an open source project, I think. So in terms of widespread adoption, I think I've been thinking about a taxonomy about what factors make things easier or hard for people to adopt. So I think the easiest case is when the use of the hardware component or tool is already checked by other tools. So the great example of this is automatic place and route. You run the APR tool, but then there's all these other checker tools that you run that confirm that the APR tool did the right thing. And so as long as you make your APR tool compatible with all those things, then actually you have a pretty good story for having people trust your tool. On the other hand, something like parasitic extraction is super problematic because how are people going to trust you without just, you know, buying a commercial tool and then matching to it? And more of a medium case is error tolerant use cases. So this is the idea that, like, yeah, your open source hardware in the beginning, it may not be perfect, it may have bugs, but the kind of systems they're putting into it, your hardware into, are error tolerant, and you can very easily work around those bugs. So maintenance cores for GPUs are an example of this. Test chip infrastructure, research infrastructure, course infrastructure, all of these things are pretty error tolerant. So this is a good starting place for a lot of open source projects. And you know, the general idea is that if you have vertical integration, then the other layers of the stack can insulate you from those bugs. So I think that's actually a very promising area for a broader class of projects than the automatically checked category. The hard category, I think, is systems that cannot tolerate errors and that, you know, cannot be automatically checked. And, you know, really hard would be things like you're guaranteeing that this thing is secure, and things like, you know, hold time, guaranteeing that hold times aren't being violated, tools that are involved in our process, like parasitic extraction, timing analysis tools. There, you know, you're going to really need a lot of time and a lot of users and error tolerant use cases to build towards the confidence for people to use systems, open source systems in this way. And so I think if you're thinking about, you know, road mapping your open source hardware project, it's probably better to focus on the easy and medium cases, unless, you know, you are working in verification technology and are confident that you can create, you know, rock hard proofs that your work is, you know, impenetrable. So I'm going to wrap up now. This is just an acknowledgement slide the various DARPA funding sources and NSF and the JUMP Ada Center. In general, though, I think the open source world is very exciting for hardware, and I'm really interested to hear your feedback for the project and for my talks.